Hello, this is Michael Radushkin, and today we're going to be looking at complex numbers, how to use them in equations, and their real-life applications. But before we begin, we must first ask, what is a complex number? So a complex number is basically a combination of two different terms, a real number, or a number that has a defined answer, and can also have a repeating decimal, such in the case of pi, or the square root of 15, and imaginary numbers which do not have a defined answer, such as I, which is equal to the square root of -1, that in a calculator would give you an error. So a complex number is the combination of these two terms, such as in the case of 3 plus 2i. Now, this format is very important, that we put the real number first before the imaginary number, because that's just the standard format when you're solving all of these equations. So now that we know what a complex number is, let's use it in an addition problem. So in this case we have 5 plus 2i plus 7 plus 12i. Now remember, as I said previously, I is equal to the square root of -1. So in order to add, all we simply have to do is combine like terms together. So the real number and the real number, so 5 and 7, and the imaginary number and the imaginary number, 2i and 12i. So if we write this out, by putting the like terms together, we would get 5 plus 7 plus 2i plus 12i. Now, what we simply have to do is combine these terms together. Now, 5 plus 7, that's obvious, that gives us 12, but when we're combining imaginary numbers together, the key rule here is just to add the number before the I. So it would simply just be 2 plus 12, and then you put the I afterwards. So we would get 12 and 14i, and that's our answer, 12 plus 14i, remembering to put the real number first and then the imaginary number. So this is all pretty simple, so now let's move on to a subtraction problem. So a subtraction problem is pretty similar to an addition problem, but we do have this subtraction symbol between these two phrases. So what I like to imagine is that this subtraction sign has a 1 in front of it. Let me get my pencil. A 1 in front of it. So it's like -1 times this phrase right here. So what you would do is simply just distribute this -1 here and this -1 here. So once we distribute it, what we have left is -3 plus 3i plus, because now we got rid of that -1, plus -7 plus 2i. And now we do the same thing that we did in the last problem and simply just combine the like terms. So we would combine -3 and -7, and also combine the imaginary terms 3i and 2i. And so in the end our answer would be -10 plus 5i. So now we will move on to a more complex but easy to understand multiplying and dividing. Right, so now let's look at multiplying these complex numbers. So here's our example, 3 plus 2i times 1 plus 7i. Now before we begin, just a reminder, I times I is equal to -1. The square root of something times the square root of something will just give you the term that's underneath that square root. So in this case it's like -1, the square root of -1 times the square root of -1 will just give us -1. That's very important when we're going to be doing these multiplication and division examples. So what we have to do when doing these multiplication problems is basically FOIL them. So we would be multiplying 3 and 1 and 3 and 7i, and we would also do 2i times 1 and 2i times 7. So if we write out all these multiplication equations that we had, it's going to give us 3 times 1 plus 3 times 7i plus 2i times 1 plus 2i times 7i. So now we basically have to work all of these out, and then we'll add the like terms together in the end. So 3 times 1, that's simple, that's just 3. 3 times 7i, as I said before, when it comes to combining terms like this, you would just combine the term that's in front of the I, so we would just do 3 times 7 and then put the I at the end, so that would give us 21I, and then 2I times 1, that's just 2I, and then 2I times 7I. Now, as I said previously, remember that an I times an I will give us a -1, so if we multiply the I and the I separately, we'll get -1, and then we multiply that -1 with the terms in front of it, so we would multiply 2 times 7, so that's 14. 14 times -1, that's going to give us -14, so we would that's the answer to that. And then simply we would just combine all the like terms together, making sure that we put the real number first before the imaginary one, and we will get -11 plus 23I, and that's our answer right there. So next we're going to move on to dividing the numbers. That's a little more complicated but easy to do. So now we're going to do dividing, which is considered the hardest operation when using complex numbers. So before we begin with this problem, there's 2 reminders that we should know. That the opposite of a plus bi, a referring to the real number and b referring to the coefficient before the imaginary number, is the opposite of that is a minus bi, simply just changing the sign in the middle and making the imaginary term negative. Another reminder that we have to know that if we're multiplying these opposites, that's the equivalent of just squaring the real number and squaring the coefficient before the imaginary number. So now let's look at this problem, 3 plus 2i over 4 minus 3i. We cannot leave this 3i here because you cannot have an imaginary number in the denominator. So what we'd simply have to do is multiply this by its opposite. However, if we're going to multiply this by its opposite, we have to also multiply that opposite at the top and the numerator. So if we were to write this out, what we would have is 3 plus 2i times the opposite of 4 minus 3i. Since we're going to do that at the bottom, we're also going to do it at the top. So 4 plus 3i. And then we're also going to do that at the bottom. 4 minus 3i times its opposite, which is 4 plus 3i. So, and let me just draw in the little fraction bar here. So, now that we have it, now that we determined what we have to multiply it by, let's start with the denominator, 4i minus 3i times 4 plus 3i. And simply, as I stated previously, that when we multiply opposites together, it's simply just the a squared plus b squared. So, in this case, what we would have is just 4 squared plus 3 squared. So 4 squared plus 3 squared. And that's going to give us 25. Because 4 squared is 16, 3 squared is 9, 16 plus 9 is 25. So now let's look at the numerator. Now, this looks awfully a lot like the multiplication. So what we have to do is just FOIL it. So if we write this out, it would simply just be we have to multiply the first term by the other 2 terms in the second complex number. So we would do 3 times 4 plus 3 times 3i. And then we also have to do it with the second term in the first complex number. So we would have 2i times 4 plus 2i times 3i. So now let's go through all of these and multiply them together, and then we're going to combine the like terms. So 3 times 4, that's 12, plus 3 times 3i, that's 9i, plus 2i times 4, that is 8i, plus 2i times 3i, and remember, like we said previously, I times I, that's going to give us -1. -1 times 2 times 3, that's going to give us -6. So, if we combine like terms together, we're going to be given 6 plus 17i. So now we have both our numerator and our denominator, so let's just put them together. So 6 plus 17i over 25. And let me just draw in the fraction bar here. But remember, like I said previously, we have to put the real number first be, we have to put real numbers separately and then the imaginary numbers. So we're going to have to split this up, and that's very simple to do. All we have to do is just do 6 over 25, and then we'll just add it on to 17i, not 12i, 17i over 25, and then just put a little addition sign in the middle. So we'll have 6 over 25 plus 17i over 25, and you could also move the I down here if you would like to. And so now we're going to look at the real-life applications and why this is important to know. So you probably are wondering, why are complex numbers so important? When am I going to use this in the real world if we're using imaginary numbers? However, complex numbers are extremely important in very complicated fields. So I highlighted only 2 of these fields, but there are many, many careers that complex numbers are very important. So first, electrical engineers, when they're trying to understand currents and how electricity flows, it's not one-dimensional. There are many factors that go into it, like I described here. Current resistance, amplitude, direction, like phase shift and frequency, all these different factors have to be played in order to understand how electricity will flow and different aspects of electrical engineering. So complex numbers make these processes much easier by giving us another dimension to work with, and limiting the amount of numbers that we have to work with, making it so much easier. And it's the same case with quantum physics, where they don't know exactly where a quantum particle's location is, and they have to use it in terms of probabilities, and they have to look at it on a 3-dimensional scale rather than a 2-dimensional scale. So complex numbers basically simplifies it again, because it gives them that 3rd dimension, and they don't have to work with so many numbers to determine kind of the probabilities of the particle. So overall, complex numbers are very, very useful in making very complicated fields much easier by giving them just another tool in order to simplify problems. So that's it with this presentation on complex numbers, and I hope that you enjoyed the video.